So, dear students, we will start today the different laws of physical modeling, and we will see that what are the dimensionless numbers which are involved in the fluid mechanics and how those numbers can be utilized in order to physical model the system. So far as the different dimensionless numbers are concerned, in the fluid mechanics, all those dimensionless number depends on the nature of forces which are acting in the fluid system, such as forces due to inertia, forces due to gravity, forces due to surface tension, forces due to pressure, forces due to the compressibility. These numbers are involved in all those dimensionless numbers which are I am going to tell you in the today's class, and later on we will see that how the concept of physical modeling can be extracted by the virtue of these dimensionless numbers. So, these are the prime things or prime objective which needs to be fulfilled from today's class. So, let us come to this is our fifth class on transport phenomena, TP 5. And the topic is non-dimensional numbers, or dimensionless numbers. And the second part of our study today, that is the physical modeling. As I have said you, the nature of different kinds of forces which may be active in the fluid system. So, the different types of forces involved in fluid flow are related with inertia, gravity, compressibility, compressibility is a thermodynamic term which is defined as beta is equal to minus 1 by V delta V by delta P at constant temperature. That means the variation in the volume of the fluid with respect to pressure at a constant temperature divided by original volume is what is known as the isothermal compressibility of a fluid. This isothermal compressibility plays a major role in order to dictate the compressibility force or force due to the compressibility during the fluid flow. Later on we will see that how this number can be utilized in order to arrive the different dimensionless numbers involved in a physical modeling exercise. So, compressibility, forces due to surface tension and forces due to the pressure difference, these are the different types of forces involved. And non-dimensional numbers involved in the fluid mechanics or transport phenomena, non-dimensional numbers involved in transport of momentum are generally the ratio of two or more of the aforesaid forces. in many dimensionless number we will find that force 1 divided by force 2 into force 3 by force 3, again it is dimensionless number. That is why I am saying there is involvement of 2 or more of the aforesaid forces. And some of the representative dimensionless numbers, are, first is the Reynolds number, it is defined as inertial force divided by viscous force, So, the inertial force can be represented as rho v square d square. V is the velocity and d is the characteristic dimension. V square d square divided by viscous force is mu into v into d, that is equal to rho v d by mu. This is your definition of Reynolds number. In any circumstances, if your viscous force is much persists, what will happen? When this condition persists, then such type of flow, such a flow is called creeping flow. Such a flow is called creeping flow. And if the inertial force in magnitude is much larger than the viscous force, inertial force in magnitude, if it is much larger than viscous force, then this type of flow is what is called the inviscid flow. Such a flow is called inviscid flow. Also, this Reynolds number has a utility in order to define the transition point from laminar to turbulent region, depending upon the density of the fluid that is flowing, or the density of the liquid metal which is flowing, the velocity of liquid metal, the characteristic length through it had to travel, the dynamic viscosity of that liquid metal or that liquid or that fluid dictates that at which Reynolds number the flow will change from laminar to turbulent or turbulent to laminar or vice versa. So, transition of laminar, transition between laminar and turbulent regions can be decided by this number. If you are utilizing this number, you can easily decide that at which Reynolds number the flow will be laminar, and after a certain critical value the flow will become turbulent. Another is the next is the Euler number. Next is the Euler number. Next is your Euler number. It is abbreviated as n suffix EU. This is called Euler number and it is defined as divided by inertial force, divided by inertial force. So, the pressure force will be equal to delta P, that is the pressure difference, into characteristic dimension square divided by inertial force is rho v square d square. So, it will come as delta P upon rho v square. Delta P here is the pressure difference between at local point and in free stream, because there must exist a pressure difference between a local point which is chosen in physical modeling as well as the pressure existing in the free stream. The difference in the pressure at 2 points is what is called the pressure difference. So, the delta P, that is the pressure difference divided by density into the velocity square, is what is called the Euler number. This Euler number is utilized in aerodynamic model testing. Different aerodynamical model testing is being executed by taking the help of this Euler number. Next is the Froude number. Denoted by NFR. This is defined as inertial force divided by gravity force, that is equal to rho v square d square divided by rho into d cube mass into g, that is equal to d square. This will get cancelled, that is equal to v square divided by g into d. This is your Froude number. This number is utilized to study flow with free surface effects, example in open channel flow. Also, the study of flow around the ship in the ship moving in the sea can be executed by this number. So, this is all about your Froude number. Next is the Weber number. This is denoted by the letter NWE, and this Weber number is defined as inertial force divided by surface tension force. Inertial force divided by surface tension force. So the inertial force will be rho v square divided by surface tension force is sigma into d, because surface tension is a force which is measured along the length of the film. So the rho sigma into d, that is equal to rho v square d divided by sigma. In the metal processing such as spray forming, atomization processes, etc., the formation of droplets, liquid droplets, and their behavior can be analyzed by using this number. Also, flow of thin film liquids, in which there is an interface, where there is an interface between two different fluids, can be analyzed or can be characterized by this number. Weber number is greater than 1 for flow of water in a river. That means flow of water in a river is an open channel flow. The Weber number must be greater than 1. The next number is the Mach number. Next number is Mach number. Next number is the Mach number. This is denoted as NMA, and is defined as inertial force divided by compressibility force. This number is used to characterize the compressible compressibility, to characterize the compressibility effect in a fluid flow. Mathematically, this Mach number can be represented as velocity divided by under root E nu divided by rho. Here rho is the fluid density. Here rho is the fluid density. This quantity E nu is called the bulk modulus. And v is the velocity. If you take the square of this Mach number, then again it is a dimensionless number. This is called the cavitation number. And this is represented as NCA. Cauchy number. It used to study cavitation, but it is called Cauchy number. It is called Cauchy number. And that is equal to, that will be mathematically equal to how much? Rho v square divided by E nu. If the value of the Mach number is lesser than 0.3, if the value of Mach number is less than 0.3, if the value of Mach number is less than 0.3, then inertial forces due to the motion of fluid is of such a low magnitude, that it cannot cause any significant change in the density, so that it cannot cause a significant change in density of fluid flow. And when this happens, that means there is no appreciable change in the density by the virtue of this motion of the fluid. Then the compressibility of the fluid, then it is customary to neglect compressibility of effect, neglect compressibility of fluid. This thing can be utilized in order to design the supersonic jets. This Mach number can be utilized. So, these are the numbers involved in the, some of the numbers involved in the momentum transfer or the fluid flow. Now come to the second part, that is our modeling, physical modeling. Come to the second part of this class, that is the physical modeling. Physical modeling. If a dimensional analysis indicates that a physical problem is described a relationship by relation between different associated pi groups, visualized as pi 1, pi 2, pi n. Okay. A physical problem, let us suppose you have conducted the dimensional analysis for that physical problem, and by the virtue of the utilization of the Buckingham pi theorem or the other methods of the dimensional homogeneity, you have obtained some of the pi groups which stand responsible for affecting that physical phenomena or that physical model. Then for a full dimensional similarity to occur, happen between the model and the prototype, scales. What should be condition? The condition should be the pi 1 for the model, that should be equal to pi 1 for the prototype, pi 2 for the model, that should be equal to pi 2 for the prototype, so on, pi n for the model, that should be equal to pi n for the prototype. This is the condition for full dimensional similarity to happen between the model and the prototype. Now the questions arises that how many types of model are there, number one, and second one, what are the different scales which can be utilized in order to characterize a model or in order to physical model a process of physical model and equipment. So, there are different scales are there. So, prior to that we should understand what are the different types of model. types of models. Basically, there are two types of model. First is the undistorted model. Undistorted models. These undistorted models are defined as scale ratio for the linear dimensions of the model and the prototype are same. That means, let us suppose the scale ratio for the linear dimension of for the model, let us suppose this is half, then the scale model for that linear dimension for the prototype should be also equal to half. When this condition persists, such type of model is what is called as undistorted model. These models are easier to study. Second one is the distorted models. Distorted models scale ratios for the linear model and prototype are not same. Then this is called the distorted models. So, in order to visualizing a difference between the distorted and undistorted models, it is customary to understand what are the length scales which are utilized in a physical modeling. So, the next topic is model scales. The second is the model scales. Let L1 and L2 are the two length variables so the requirement based on the pi terms for these variables, क्या कंडीशन होना चाहिए? What should be the condition? The condition should be the L1 for the model divided by L1 for the prototype, that should be equal to L2 for the model divided by L2 for the prototype, and so on. It is called lambda L. This is called length scale. This is called length scale. Okay. Other scales may be velocity in the model divided by velocity in the prototype. This is called the velocity scale, lambda v. This is called velocity scale, right? Density of the fluid in the model divided by density of the fluid in the prototype. It is called lambda rho. This is called density scale. This is called density scale. Kinematic viscosity of the fluid in the model divided by kinematic viscosity of the fluid in the prototype, that is called lambda mu. This is called viscosity scale. Viscosity scale. All such scales need to be defined. What will happen in the many model study? The question is now, in order to have an insight of what basically the distorted model is and why it creates so much difficulty, in order to physical model a process if undistorted models are there. So, I would like to make you understand that what is the difficulty if the full dimensional similarity is not occurring in the case of distorted model. What should be done in that case? So, I am giving you an example. In many model studies, one or more similarity requirements may not met. That may not be equal, that with respect to this scale. When this condition persists, that in many model studies one or more similarity requirement may not met, then such models are called distorted models. As an example, if you are studying the open channel flow in a river, if the depth of the water in the river is very high or very uneven, then it is impossible in that case to adopt the same scale ratio for every dimensions. So, under those circumstances, such type of modeling is based on the modeling of the distorted models. But on the contrary, let us suppose on a live scale you are measuring the length or depth of the water with respect to very small distance created on a live scale, then in that case the model ratio may be maintained. So, in many practical problems, basically the concept of undistorted model comes in the picture. So, an example of this is the study of free surface flows. So, let us continue our study of the free surface flow. Study of free surface flows. Both Reynolds and Froude numbers are involved. Okay. In this type of study, both Reynolds and the Froude number are involved. So, let us consider the similarity with respect to this Froude number. Let us consider the similarity on the basis of Froude number. So, the Froude number similarity for the present circumstance Froude number similarity gives this Froude number should for the model that resembles with the Froude number for the prototype. That means Vm divided by Gm dp, let it be a, I am denoting here the characteristic dimension is L, let us suppose. So, this that should be equal to velocity in the prototype divided by under root Gp Lp. So, the ratio Vm divided by Vp, that should be equal to under root Gm Lm divided by Gp Lp, that should be equal to Gm divided by Gp under root Lm divided by Lp, that should be equal to under root Lm by Lp if model and prototype are under same gravity condition. Only then these two acceleration due to velocity can be considered as equal, or Vm divided by Vp, that should be equal to Lm by Lp. And what is the value of Lm by Lp? What it is called? The length scale. That is called length scale. That is under root lambda L, that is lambda L raised to the power half. Let it be question number 1. This is the condition which have been arrived by the equality of Froude number in the model as well as in the prototype. Now, Reynolds number similarity, Reynolds number similarity gives rho m, here you should write n Reynolds number for the model, that should be equal to Reynolds number for the prototype. So, rho m Vm Lm divided by mu m, that should be equal to rho p Vp Lp divided by mu p. So, Vm by Vp, so Vm by Vp, that should be equal to rho p LP mu m divided by rho m Lm mu p, is it not? Right? So, it can be written as mu m divided by rho m divided by mu p divided by rho p, this quantity, and what is left out, LP divided by Lm. That this quantity mu by rho, that is the dynamic viscosity divided by density. This is another quantity, it is called the kinematic viscosity nu. 5 minutes, Sinaji. 5 minutes. So, that is equal to nu m divided by nu p into LP by Lm. Now, this quantity LP by Lm, from here we can deduce that LP by Lm is equal to lambda L raised to the power minus half, sorry, lambda L raised to the power minus 1, that is the lambda L. So, Vm by Vp, this quantity equal to lambda L raised to the power half, imply that lambda L raised to the power half, that is equal to nu m by nu p, and this quantity is equal to lambda L. One upon lambda L. So, the quantity nu m by nu p, that is equal to lambda L into lambda L raised to the power half, that is equal to lambda L raised to the power 3 by 2. Let it be question number 2. So what conclusion that can be drawn from here? The conclusion which can be drawn from here is, equation 2 states that both model and the prototype, to have different, this nu is called kinematic viscosity, whereas mu is called the kinetic viscosity. So, this nu is called the kinematic viscosity, it is defined as mu, that is dynamic viscosity divided by density. So, the equation number 2 states that the both model and the prototype to have different kinematic viscosity scales, Such a fluid is very difficult to search, and hence in case of such a distorted model, it is advisable that modeling should be executed on the basis of Froude number, similarity, Proud number similarity with different Reynolds number. Proud number similarity with different Reynolds number. With different Reynolds number. This is the distorted model study. Basically, in different situations which happen in the practical problems, you have to decide the criteria in such a manner that there should not be two length scale for any of the variable associated in that physical problem. So, depending upon the circumstances, you have to judge the condition in such a manner that which dimensionless number should exactly be used in order to arrive at the optimum results. Thank you.